Imagine diving into the ocean. As you slip beneath the surface, a strange sensation sets in: weightlessness. That feeling is created by a temporary balance between two of the most important physical forces affecting water bodies. One of those forces is gravity. Gravity is arguably the most relentless sculptor of aquatic ecosystems. It pulls water downhill, shaping entire landscapes. Rivers flow, glaciers melt, and aquifers drain because of this constant downward tug. Within oceans and lakes, gravity structures the water column itself. Denser, colder water sinks below the lighter, warmer water above, creating gradients that define these water bodies. It is not just Earth's gravity that plays a key role. The pull of the moon, and to a lesser extent the sun, drives tides that rise and fall in predictable rhythms. These tidal pulses move through coastal and estuarine systems, stirring water and shaping the flow of nutrients and energy. The pressure gradient force is arguably the second most important force acting on water bodies. You felt this force through the buoyancy you experience when floating on a boat, canoe, or paddleboard. The buoyancy of an object is created by pressure differences across the object itself, with greater water pressure pushing up on the bottom than on the top, producing an upward force that supports its weight. In the atmosphere, the pressure gradient force drives wind, which moves from areas of high pressure to areas of low pressure. And because of a third force, friction, that wind energy gets transferred into the water, sculpting the surface into waves. Whether a wave travels across the surface or seems to stand still, the size and strength of the wave depend on how much energy the system supplies and how long it lasts. For example, weak or short-lived pressure gradients like a gust of wind can create capillary waves, those shimmering patches of ripples that dance across the surface of water bodies. Moderate and persistent pressure gradients can drive Langmuir circulation cells, recognizable as streaks of foam or debris where rotating surface currents converge. These features concentrate particulate food resources into hotspots of productivity, but they can also trap pollutants like oils, microplastics, and chemical residues, increasing contamination. In contrast, strong and persistent pressure gradients can cause massive waves that crest and break. These towering waves carry enormous energy across vast distances, building until their own weight topples them into a crashing wall of water. Winds don't just cause waves at the surface of water bodies, they also drive internal waves hidden beneath. These waves often travel along the boundary between warm surface water and the colder, denser layers below, silently rocking the deep layers long after the wind has stopped or shifted. Taken together, gravity, pressure gradients, and friction form the core trio of forces that set water bodies in motion. Gravity pulls water downward, shaping landscapes and creating vertical density differences within the water body. Pressure gradients drive winds and currents, and friction links the atmosphere and water, transferring energy across the surface. Almost every ripple, current, and wave we can detect are shaped by the constant interplay of these three fundamental forces.